I wanted to do a quick summary of what we covered in lecture today with our lab activities, and we had a lot of fun. But I also wanted to make sure they get a little bit of learning done so that we sort of feel comfortable with what everything has been about for the week. So we started off lab, if you remember, with having just this little bowling ball on a surface. And of course, when it rolled, it hit the ground and boom, it stopped. And what we really sort of examined on a closer level is that when you take a bowling ball and you magnify it, its surface on a microscopic level looks really bumpy. So again, bumpy on a micro level. And the other thing is that the floor that it rolls on is also bumpy. And what this means is that bumpy on bumpy means stuff slows down as it moves. And the way we were able to actually see this was that we asked ourselves a hypothetical question. We said, okay, if you roll a bowling ball on a desk and it comes to rest, or if you roll a bowling ball on a desk and it's a perfectly smooth bowling ball and a perfectly smooth desk, what would happen? And what we realized is that smooth object on smooth surface keeps moving, which is really cool when you think about it, because my intuition says, okay, when something is moving, it should continue moving. But of course, a couple questions arise. One question is, when you say moving, the first question that comes to my mind is, well, how does it move? Does it move in a straight line? Does it turn? Does it back up? What happens? And then the other question that comes to my mind is, well, does it keep going forever? So I get it that when something's really smooth and it moves on a smooth surface, it's going to be harder to slow it down. But my question then becomes, what path does it take? Does it go just straight forever and ever? Is there some reason why it would turn? Would it maybe perhaps slow down and maybe never quite stop, just keep on slowing forever and ever? Or does it actually just keep on going just into eternity for down this crazy smooth table with this crazy smooth object? So that was the whole point of what we wanted to kind of do in lab. So what we did after sort of doing this little bowling ball scenario was that we looked at a situation which was really kind of simple when you think about it. We had our little friend the cup and our little friend the marble, which is nice. Cup and marble. And so what we did was we actually flipped the cup over and put the marble under it. And we kind of move the cup round and round in a circle. And if we're looking at this from above, what would happen is that the marble would trace this circular path. And what we realized is that when you let the marble go, so you have this marble, say, let's have it go, let's have the marble go, say, counterclockwise like this. So if I were to release the cup right here, what would happen to the marble is that it would actually go off in this direction. Just, it's barely touching the circle, but what we realized was that it would go in a straight line at a constant speed. So here's the point of the lab that I really didn't get to make today that I kind of want to start saying. A force gets something moving. Like in this case, it was the force of the cup on the marble, and we kind of got it moving that way. But then, when the force is turned off, the object from our model, from our little observation, continues to move, and we notice that it moves in a straight line at a constant speed. And so what ended up happening was we took this observation right here, so this one right here, and we took our bowling ball observation right here. And we actually said something pretty big about the Earth and the Sun. We said if this is the Sun, and this is the Earth going around the Sun, like this, what we said was if you took the Sun and just all of a sudden made that Sun, just do this, made the Sun vanish so that all you had was the Earth, what would actually happen is, based on our observation of the bowling ball, well, there's no surface for the Earth to be rubbing on. It's in the middle of outer space, and there's nothing in outer space. And the Sun vanishing is kind of like the cup disappearing. So when we put this idea together with this idea, what we conclude is the Earth breaks out of its orbit and goes in a straight line at a constant speed forever and ever and ever. That's a really weird idea. If we take this idea here and put it together with the bowling ball idea here, we get this really weird conclusion, which is that if an object's moving, if something moves, it doesn't stop. It goes on forever and ever and ever. That's the weird part about what we saw today. And of course, there's still room for skepticism and there's still room for doubt. One of the best versions of this question I heard was somebody asked me, they said, once you stop pushing, shouldn't the force wear off after a while? So that, yes, okay, I get it that you get a big force on something, you're going to get it moving, but then shouldn't that force somehow wear off after a while? So then what we decided to do to put this entire idea to rest was we played some air hockey. And here's what we did. We had our little table, right? A little table here. And what do? We played air hockey with a ball of paper, right? We had these awful erasers. Block 3 actually literally asked for the torture to stop. And we had a nice hunk of, so we had paper, eraser, and dry ice. And of course, here's what we noticed. When we played air hockey with paper, it was only fun if you cheated. Because the paper would slow down. It wasn't, it would go all over the place. It was slow and it was boring. When we tried playing with the eraser, it was even worse. It was the most boring game ever because when you pushed the eraser, there was so much friction. The game was just terrible. And finally, when we played with dry ice, we noticed something. The game started off slow. But then what happened is, like if you had the dry ice kind of bumpy on the bottom like this, after a while, this would start to evaporate. And then after a little while, you'd have this piece of dry ice. And what would happen to it is part of it would start to evaporate. And you'd get this really weird thing where the bottom would kind of smooth out and evaporate away. And if you flipped your ice over, you notice this almost super flat surface. And what would happen is it was so smooth, and the cushion of CO2 provided air, or not air, but carbon dioxide gas, so that the thing was barely touching the table, that when you hit it, it would go for a really, really long time. Why would I mention something like this? The reason is this is exactly the experiment that Galileo Galilei did when he was talking about his idea that we've now come to know as inertia. And Newton, a little while later, was actually to write up all the results that we have from our lab today he was actually able to write it up like this. And this is what we call the law of inertia. First, an object at rest stays that way, stays at rest unless an outside force makes it move. Sometimes you'll also see this word written as unbalanced. I don't care how you write it for now. I'm going to probably this semester stick to unbalanced. Unless an unbalanced force makes it move. And I think most people who read this, they're totally fine with it. But here's the weird part about our work today. After all the lab work that we did in class today, we came to an even weirder conclusion that's totally counterintuitive, but it was absolutely borne out by our observations and our evidence today, which is if something is moving, it continues moving forever in a straight line at the same speed until an unbalanced force changes things or comes along. So we got two rules. One is if something's at rest, it wants to stay at rest. But here's the weirder part. If something's moving, it will stay moving. We saw that with the dry ice. So we thought things like, oh, the paper must want to slow down because of something in the paper. Or the eraser must want to slow down because of something in the eraser. And then when we really played around with the dry ice, any intuition that we had about this was just destroyed. And we realized, wow. When you get something moving, what slows it down is the fact that it's got little bumps that make it bump against surfaces, and there's a force of friction that slows things down. What really happens is that if you get something moving, it's going to stay moving like that forever and ever and ever in a straight line at a constant speed. This property of matter is known as the law of inertia. And that was what this last class that we did today was all about. So that wraps up our coverage of the first law. So if we cover this and we get our free body diagrams mastered, which we'll see in the next video, that's pretty much what I want to cover for this unit before the final exam.